In this lecture session, I will be talking about Ampere's law. Now, what is Ampere's law? Ampere's law states that the line integral of the tangential component for the magnetic field intensity around a closed path is the same net current enclosed by the path. So what does this actually mean? So better if we represent it as a mathematical equation. Ampere's law basically states that if you have a magnetic field intensity and you integrate it over a closed line, so closed line, then you will get the total current enclosed by the closed line. So if you check the units for H is ampere per meter. If you integrate over a line, then you'll get meter. So the meter cancel out and you get the total current in amps. Now we play a bit with mathematics. From Stokes' theorem, we know that if we have a closed line integral, is equivalent to the curl of the vector integrated over its surface area. So by knowing this, we can also relate with another equation that we have already learned from electrostatics, which states that the total current is equal to the surface integral of current density J. The unit of J is ampere per meter squared. When you integrate over a surface area, meter squared, this variable gets cancelled and you get the total current amps as well. So notice the similarity between this part here and this part here. Since both this part and this part can be used to calculate the total current enclosed by a surface, by a line, so we can conclude that del cross H equals to J. This is a convenient equation that describes the relationship between magnetic field intensity H and current density J. So if we have one, we can find the other using this relationship. So Ampere's law is equivalent to Gauss's law. It is a simplified law that can be used when the current distribution is symmetrical. Okay, so when the current distribution is symmetrical, we have an alternative, easier way to find the magnetic field intensity H. And since we know that B equals to mu H, we can then also find the magnetic flux density. So, symmetrical conditions only exist under a few special conditions. So these are the example of special condition. Number one, infinite line current. Number two, infinite sheet of current. And number three, infinitely long coaxial transmission line. Note that if the current distribution is not symmetrical, then we need to revert back to the use of Biot-Savart's law. Furthermore, the current must flow through a closed path to be able to, for us to be able to draw the Amperian contour, much like for electrostatic, we have Gaussian surface to apply Gauss's law. So we need to be able to have this Amperian contour. So the figure here shows a depiction of an Amperian contour. So for figure A, the current is enclosed by the circle here. So the current, because we have a dot at the middle, the current is coming out of the page. So if you use your right hand rule, your thumb should point to yourself and your four fingers will point to the direction of the magnetic field. So as you practice this in front of the screen, you notice that on the left hand side, the magnetic field will tend to go downwards, and the magnetic field for the right hand side will tend to go upwards. So similar to figure B, although the shape is a bit uneven, still the current is enclosed within the line. So still we get a rotation of the magnetic field intensity in a sense. But for figure C, the contour is outside, or the current source is outside the contour that has been chosen. So as you can see, because it's outside, so the direction of the magnetic field intensity on both sides of this contour is moving upwards, because the current is located outside the contour. So in this condition, we cannot apply Ampere's law. So let's look how Ampere's law simplifies the calculation under the symmetrical condition. So a long straight wire, assume that is infinitely long with a radius A, carries a steady current that is uniformly distributed over its cross section. So determine the magnetic field H at a distance R from the wire axis for two conditions. Condition 1, the distance is less than the wire's radius. And condition 2, the distance is further or larger than the wire's radius. So let's look on how to solve this problem. So we have a conductor or a wire. So this is the cross section of the conductor, and this is the front view of the cross section. So we want to calculate the first condition, R smaller than A, where A is the radius of the cross section of the conductor. So now we refer to the green dotted or green dashed lines here. So remember that the current is evenly distributed across the cross section. So for R less than the radius A, we apply Ampere's law. Ampere's law states that the closed line integral of H is equal to the total current enclosed by the line. So we replace the equation. So to get a closed line integral, we need to integrate over the whole circle. So the whole circle is 0 to 2 pi, which is 360 degrees. Now, we have H1, and we have the differential length of this line here is equal to R1 d phi, and it's in the direction of phi. Similarly, H1 also is in the direction of phi. So phi dot product of the same direction, you're going to get 1. So you're going to get H1 R1 d phi integrated between 0 to 2 pi is equal to I1. So when you integrate, you only need to integrate over phi. So basically, you get 2 pi R1 H1. So 2 pi R1 is actually the circumference of these green dashed lines here. An important thing to note that the current I1 flowing through the area enclosed by C1 is equal to the total current multiplied by the ratio of the area. So if R1 is less than A, the total current is a ratio of the current flowing inside the green dashed lines divided by the current flowing in the whole conductor. So since the area is given for a circle is pi r squared, so I1 is equals to pi r1 squared, the area of the small green circle, divided by pi a squared, the area of the conductor. So we can cancel pi and pi, okay, and then we need to multiply with I. I is the total current flowing in the conductor. So we can cancel pi and we get R1 over A, and we take the square out to get this portion here. Now we replace this part in this part here, and we already know that H1 integrate over the line is 2 pi r H1. So we get 2 pi r1 H1 equals to r1 over a squared multiplied by I. And we take 2 pi r1 to the right hand side. So we get r1 divided by 2 pi a squared multiplied by I. So this is the general equation for R1 when R1 is less than the radius A. So let's look for the second condition if the distance R is larger than the radius. So if the distance is larger, we still get the same format of the equation. Integration of H2 dL2 equals to 2 pi R2 H2 equals to I. But now the difference is, if we refer to the previous figure, now if R is larger than A, then we refer to this blue or purple dashed lines. So even as the distance or the size of this circle becomes bigger, the total current does not change. The total current is always the amount of current that is flowing inside this conductor, no matter how large this circle is. This is different from the previous case where R is smaller than A. As R1 increases, then current increases until it reaches the maximum value when R1 equals to A. So going back, so I is now constant. There is no more ratio like the previous derivation. So we can get in the form of H2, we take 2 pi R2 to the right hand side. So we get this equation here. H2 in the direction of V is equal to I divided by 2 pi R2 in the direction of V. So when we replace a value, let's say we have a current I equals to 1 amps, and these three conditions here, the radius is 10 centimeter, R1 is 5 centimeter, and R2 is 15 centimeter. So the first case we replace with H1. So R1 is 0.05, we convert into meters. A is 0.1, and we get 2.5 over pi. I purposely keep it in the form of pi, but you can divide with 3.142 if you choose to do so. Next, what if we have R equals to A? Then in this case, we have the equation here where we can cancel A on the top with A squared at the bottom to get I over 2 pi A. And by replacing, we get this value here, 5 over pi. So next, for R equals to 15 cm, we just replace the equation where R2 equals to 0.15 and we get 3.33 over pi. Now let's say we calculate for every value from R1 equals to 1 centimeter to R2 to let's say 20 or 30 centimeter. We start for every 1 centimeter increment. So 1 centimeter, 2 centimeter, 3 centimeter, and so on until let's say 20 centimeter. So for every centimeter, we will see a pattern like this. So if R is smaller than A, then it will increase linearly as the distance increases from the center of the conductor's cross-section. So in this case, because if I take A equal to 10 centimeter, so from 0, 1, 2, 3, 4, 5 up until 10 centimeter, the magnetic field strength is going to increase linearly. Now at 10 centimeter or when R equals to A, you are going to have the peak magnetic field intensity, which is in this case 5 over pi. Once we go beyond this, when R is larger than A, then the value of magnetic field starts to drop. As we go further away from the conductor, then of course the magnetic field is going to drop. This is logical because if you are trying to measure magnetic field from a current carrying conductor, the further you are away from the conductor, the weaker the magnetic field strength. So that is represented by the downward slope here. Now let's look at the second example, magnetic field inside a toroid. Now what is a toroid? A toroid is actually coils that is wound over usually a magnetic material like iron. Okay, in actual or in reality, these coils here are tightly wound close to each other. But for this figure, we just want to show, or we want to represent and see the direction of current and the magnetic field. So toroids practically are used to magnetically couple multiple circuits and to measure magnetic properties of materials. So let's say we have a coil here, a toroid here, and there's a coil surrounding the toroid. So it's shaped like a donut, right? And it's made of ferromagnetic material. So the current is flowing this way, so circular. So if we have this condition, for a toroid with N turns carrying current I, we want to determine what is the magnetic field H in each of the following three regions. Number one, the distance R smaller than the inner radius A. Number two, R is between A and B, which means it's inside the donut-shaped ferromagnetic material. And for R larger than B, which means outside here. All in the azimuthal symmetry plane of the toroid. Azimuthal means phi angle. So it refers to the cylindrical coordinate. We have phi. Phi is measured on the xy axis and is measured in the direction from x-axis to y-axis. So imagine if you have x-axis here, horizontal, y-axis here, vertical. So phi is measured from x to y. That is why you see phi here. Okay, in the counterclockwise direction. Whereas H, if you use the right hand rule, where your thumb points to the direction of current, then you will identify that the magnetic field produced will move in the opposite direction to the direction of phi. So it's going to move clockwise. Right, so how do we solve this kind of equation or this kind of problem? So let's look at the simple part first. Anything inside the toroid or outside the toroid, the magnetic field is going to be zero. Why? So for the internal, the radius or the distance inside the conductor, there will be no magnetic field because there is no current or flux flowing inside it. That's why H is zero. Where when R is larger than B, means it encloses everything, then the total net flux coming out of the conductor and the total flux coming in back from the coil is always going to be equal. So we have the net flux is going to be zero. And since if the net flux is zero, then H will also be zero. So we only need to calculate the second condition here, where R is smaller than A but larger than B. So applying Ampere's law over the contour C, we have this equation again. And we replace. Again, we have an integral. For the closed line, we have from 0 to 2 pi. Because direction of phi, so we have R dv. But now the angle or the direction is opposite. So we have phi, negative phi, dot phi. So you're going to get negative. When we integrate over 2 pi, we get 2 pi, R and H. N is equivalent to negative N. N is the number of turns, and I the magnitude of current. Therefore, we have H is equal to Ni over 2 pi R. And we have the magnitude of the, the vector of the magnetic field intensity is equal to magnitude of H in the direction of negative V, or Ni over 2 pi R in the direction of negative V for this range. So these are the two conditions where we get a very simplified equation to calculate the magnetic field intensity.